It has solutions, and this is the matrix. That's square. Chapter 4, section 4.
If it's easy.
Is it easy? No, I just
Like, if the question is not possible, like, and the answer people like, how long did you think about it? Well, after that.
I'm literally absurd.
Or like, some of these things,
That was me.
you think this course is like, just kind of, like, what?
Not just the method, not the actual answer. I tried to make it as much of times, I didn't get that. I got other things, but. I use the propositions, not that helpful. I guess the point is we learn enough that it is helpful.
Yeah, I mean, if the author tells you it's helpful, it means it's helpful. So yeah, it's exactly the point of the topic. So.
But A just means you're projecting out to one line, right? In R4, because it's just one vector.
Right, yeah, exactly. Yeah,
So don't we just project it like they got products with each of the like because you need an orthonormal set, right? So you just take 1, 0, 0, 0.
So yeah, the topic would you make?
No, I thought it'd be one by the results.
Well,
It says it has 4.
Because I want it to be one number for each of the.
Oh yeah, you're taking, that's right. Taking obviously okay.
Yeah.
Taking back to the other one.
Okay, I'll just hold it.
No, I'll hold it. Just go to the.
Ultimate God episode.
Oh.
That's the weird thing. Like I tried and I tried and I tried.
Hello,
Well, I mean,
what? No, people
We're not. Literally 1 hour. Literally 1 hour. And I took a break and came back and I said, I don't have time.
I mean, you know, the one thing about practice, it's not like,
It could have mistakes.
of course, so for me, hopefully prove the rest of the study. Because, yeah, the rest he proves it not with the
At least can you explain them like how to do it?
This is
Yeah, he did an example, but it was like basic like vectors, like unitary vectors, 1, 0, 0, 0, 0, 1. I tried that, it didn't work. I tried the formula, it didn't work. And I learned 5 pages on my it was so much.
yeah, you have to follow the example, right? So you have W,
Yeah.
then you have to extend to the basis for our B, which is gross net. Okay? So that's why it's 4 by 4, because you have to extend one vector. Or 3 by 3, whatever it was.
Okay, I have to I have to extend. Oh yeah, then I do this. Then I use the formula for projection, right? dot product xw multiplied by w, right?
Yeah, but it will just map it to 0 because it's on the complement. Otherwise, it would have been 4 by 1, but it's not because I mean that's what he wants. It's not like yeah, but he thinks that you read the example. Well, I mean the example he extended, right? So yeah, so no, that example is for a projection, orthogonal projection.
The question is question 4A.
All right. Again, just in case you're wondering, where we finish for the midterm is up to this review I made yesterday. Okay, so make sure you're very comfortable with this stuff, and especially the statements. So make sure you know why we need some ability, why we don't. Okay, remember yesterday I was staring at you for like half a minute. So, yes. Yes. That's right, yeah.
Is it any orthonormal basis? Will it be a different symmetric matrix if it's a different orthonormal basis, or is there like some sort of invariance that I'm missing?
No, I remember this being an invariant because you can see it yourself. Suppose you have some change of basis. When you start multiplying out, there's all these zeros underneath. Yeah, because it's upper triangular. Suppose you start with an upper triangular representation. Suppose you have a basis that you have upper triangular. Now take some other orthonormal basis. Then you will have a change of basis between them. So then start multiplying by the change of basis to see how the other matrix looks like, the other representation. And the zeros will start killing the, yeah. So, it's the same with the diagonal. So, like, how do you say it? I mean, okay, let me rephrase this. Like, oh, you want for any orthonormal basis? Oh yeah. Okay, you can hear, like right here, this fails. Forget about the upper diagonal. Oh no, this is non-orthonormal. Okay, no. Of course, it fails. Like you can have matrices that you diagonalize. The definition of diagonalize is that you can find an orthonormal basis. Well, I mean, yeah, but yeah. That's why diagonalizable is a whole thing, because you start with something non-diagonal. And after you change your basis, you make it diagonal. So this is the same thing for upper triangle. Yeah, so we're gonna finish today this criterion, namely, so remember again the spectral theorem for reals. You need the multiplicities to be equal, geometric and algebraic, and but you also needed the summability, which is trivially true over the complex numbers, because you have you have n complex roots. But anyways, over the reals, you might not have the thing splitting. So for this guy, if you take this to be n, p of n lambda is equal to lambda squared plus 1. So this guy only has the plus minus I roots. So this guy is not splitting over it. So this matrix here does not have upper triangular representation. Okay? Huh? No what? Yeah, you must, exactly. All the roots need to be real and they have to be n of them. I mean, okay, all of them. So yeah, n of them. Up to with multiplicity. Right. So we went through the technical result last time, but I'll review it. So here, we proved the following technical result that if you give me a map T whose polynomial splits, so only real roots, and you give me an invariant subspace, then I can add an eigenvector, so this will be an eigenvector, from the complement, so that x plus w is still T invariant, meaning x plus w gets mapped inside x plus w. Okay? So we proved that last time. And I'll just use it because the proof was very technical and it's hard to restart. So let's prove our main result. So namely, I will show that if PT has only real roots, then your map T has there's a basis that exists beta such that T beta is UT. So also normal. So some beta, not for all beta. Yeah. So that's what we're going to prove. And yeah, so PT has D roots in F, but we really need R because for complex, this is median. And wait, I'm still doing the proof. Oh, we talked about this. Sorry. Right here. So same result. PT splits get that T beta is UT. Right. So I do both directions. First, I assume that there is such a basis. I'm going to prove to you that the polynomial splits. Zoom people, copy. So yeah, there is some basis that you can manage like this with eigenvalues on the diagonal. Okay. And can someone tell me how to finish from here? That PT has only, so this is, yeah, has only real roots. Any idea? Just to see if you understand the definitions. It's not a tricky, not a trick. It's not a tricky question. Yeah. So yeah, but what is PT? I just want to see if people remember. So what's PT? Okay, so it's not that good. So PT lambda is the determinant of T minus lambda I, and it's invariant under the basis. So you can take this basis here. beta, okay? And then, yeah, then you stare at this matrix, and it will be what? It will be the determinant of lambda 1 minus lambda n minus lambda stuff 0, which is exactly what you said. N. Is that okay? Now, let's do the harder direction, namely the interesting one, where if you can show that you have only real roots, then you have a nice upper triangular representation. Right, we showed before that upper triangular is easier to work with when you have a chain, namely you can build a sequence of subspaces containing each other all the way to the total space V. So that you have T invariants. So TW1 is inside W1. You know, I don't know, it's like a Russian doll. I know Russian is unpopular, but like, right now this is a good analogy. And you map inside to inside. Okay. Okay. All right, so we have to build this. Once you build this, you get your upper triangular. So we're going to do this by induction. We will build these guys one by one using that result from before, namely that, okay, I'll also do. So you start with W1, and since your guy splits, there exists at least one lambda 1. Well, it could be the identity now, right? So they will all be, lambda 1 will all be 1 for all I know. So there's no lambda 2, lambda 3, lambda 4. They could all be one guy. All right, good. So, but that's all you need. You just need one real eigenvalue and you build from there. And right, so there's just an x so that Tx is lambda 1x. All right. Now let's assume by induction that you build everything up to k minus 1. Okay. And now you want to go to wk, the very next level. Meaning I have a chain w1, w2, blah, 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 wk minus 1, and I know that wi is inside wi. So if you like, my matrix so far looks like this. So you take the basis for W1 and basis for W2, take away W1 and the basis for, so like you keep taking complements, call this B and grow it. So that is a basis for V. Okay. Then you have that up to B, your upper triangular. But then the rest, you're still like stuff. Okay. As of now, I have to make a good choice of A to make it upper triangular. Okay, good. So we talked about that. Right. So by induction, because otherwise I would be done. Right? If I don't put cross here, I will be done. So assume that you haven't covered the space, so you can find an element in the complement. Okay, so you have wk minus 1, and there's an x over here inside the total space. Now, and this x, the way we picked it was that you have an invariance. So we prove this result over here. right? So you give me T C X K plus Y K minus 1, where this guy is in W K minus 1. It gets mapped to some CTXK plus TYK minus 1, where this guy is still in the span over X, and this guy is still in the, actually was span this plus this, and this is still in WK minus 1 by invariance. Okay, so here we're using induction. And here is how we build the TXK. So maybe I have it over here. Okay. So I didn't have so the way we build TXK, let me remind you, it was an eigenvalue, some eigenvalue xk, and then we had a projection map. So it was some tilde yk minus 1. I might as well go to the proof. I have it. So how did we pick the xk? You actually have to look at the proof. So, right. So over here, that's how we picked the x. And it was that x is almost like an eigenvector plus a projection onto the previous subspace. This would be k minus 1. Is that okay? Okay, so that's how we pick the x in v take away wk minus 1. And this is important because it means it maps that x plus y business into still inside the span of x plus wk minus 1. Okay, let me go back. Yeah, so again, let me repeat because it's the same argument. So you take the span of xk plus twk minus 1, and I showed that by induction, this is inside wk minus 1, and this guy is inside span of xk plus wk minus 1. Okay, because it was the projection. Let me write it this way. There's so many ways to write this. Okay. So you project V down to WK minus 1, which is inside, which is exactly span of XK, P of WK minus 1. So together they're in the span of XK. Is that okay? Keep writing. So can somebody tell me what should WK be so that I have my invariance after I wrote it? What should WK be? So that you have this and you have this. No. Anybody know? Zoom people? Zoom people know what WK should be? What? Okay, go ahead.
The lambda, like so x it was like some x that like when you take a t of it, it's like like lambda x plus the projection whatever. How do you know that lambda is it supposed to be separate than the other lambdas that are already like have their eigenvectors in WK minus 1?
I don't remember how I picked up on
Restrictions on the lambda, so it's not already in, like, its eigenvectors are not already in WK minus 1.
No, this is not an eigenvector, because it's not Tx equal to lambda.
Like, how do you, that's my question. Is it any of the lambda? Like,
Yeah, it can be the same lambda, that's not a problem. No, it's trickier. I mean, I don't know how deep you guys are gonna go into reading the books, because they're very tricky, but the point is, we had this weird thing. We had determinant of t minus lambda I equal to determinant of t restricted w minus lambda I times determinant of the projection onto the complement, which we wrote as, and so I'll just write like this, minus lambda I. I mean, that's what it was, right? So it was I minus PW. So we have these mappings, and then because the guy splits, we know that this is lambda k, and we also proved the lemma that this guy divides this. So that means that the interesting part, this can be written in the same form. So P restricted I is equal to a product of this lambda k, but some subset, call it S. And from here you get that this guy has eigenvalue. You pick one of these eigenvalues, lambda I. Yeah, this will be the lambda. So put X here. It will be lambda star X. But then this guy here was, the way we picked it was I minus, and there was an S here, T was a S. But it was basically this guy, and this guy. And then just rearranged. So it was Tx equal to lambda star X plus restricted people. Anyways, yeah, but you basically showed that the projection of the map T onto W complement still has an eigenvector. It's a very convoluted argument to say that. But that outside your invariant subspace, you can still have an eigenbasis. So in a way, it is like the eigenvector. It's like an extra eigenvector from the complement of the invariant subspace. Okay, I mean, but at the end of the day, when you go and sit down on MATLAB, you just kind of put an eigenbasis down. That's all you need. All right. Anyhow, so the main result that I want you to remember is if you have the summation of mi is dim p, or pt has only real roots, then this implies that t is upper triangular. Okay? So please remember that. That's the main result. And we're going to use this many times. So, okay, good. Questions, Zoom people? All right, so this theorem, it's in itself, so it's not part of something else. So we will test you directly on the theorem called the Caley Hamilton, because it's a useful computational tool. We will use it to compute inverses. Okay, so that's what I was instructed to do, to compute inverses. All right, so in homework 4, you proved the following result that we tried with some of you. that you can always find L and constants so that this guy is 0. Okay. And the motivation for this question was exactly this following theorem. Namely that you start with some map T, you have your polynomial splitting again. Then if you evaluate PT of T, so this would be slash lambda. Okay, so T minus lambda I, when you evaluate lambda at T, it would be the 0 mapping. So I do examples just to see what this means. Okay, yeah, so if F is the complex, what can you say about this theorem? Just to see if you follow. If you know the field is complex, is this theorem hard to use? Let's just say, I want to say people follow. What do you think? I'm not sure if you guys know, or is it hard, or what? Yeah, but like this will show up where I mean, you know, if you do everything the day before, then it won't work. I was an undergrad too, so I know. But so this is the fundamental theorem of algebra. Yeah. So you always have d in v roots over f equals c. So the assumption is trivial. So it's always true. For real, it's not. All right, let's do an example. So take 2 by 2 matrices, and the characteristic polynomial is always of the form. Namely, you take the trace of the matrix, and then the constant term is always the determinant. And Caley Hamilton says that if the polynomial splits, namely you can factor this into lambda 1, lambda 2, with lambda I in the reals. Then you have this result, namely the square of the matrix minus the matrix plus its determinant with identity is equal to 0. So let's do an example. I mean, we can approve that. That we need the eigenvalues to be real. Yeah. So take this example. Yeah. I mean, you can imagine if, okay, so take this matrix, it splits. Yeah, can someone tell me why it splits? What are the eigenvalues of this matrix? So what are they, right? Yeah, 1 and 2. Because you just do 1 minus lambda, yeah, exactly. So these are the eigenvalues, so it splits. So you can apply Caley Hamilton, and you have, I should put identity here. So you have the following relation between matrices. Let me put it. So I should have written here 1, 1, 0, 0. All right, and you can do the computation. This will be the 0 matrix. If you like sit down and compute this, you will get the 0 matrix. So let's do an example to see why we need this. So we're gonna find the inverse of a matrix, like from 2 to 3, just the inverse. No reduction, none of that. So you know determinant of n is not 0 because it's invertible. And so it was in one of your homework suggested problems to show that the constant term is the determinant. or the characteristic polynomial. But you can see this immediately actually, so I'll do it here. So PT lambda is a polynomial, okay? A naught, A1 lambda, blah, 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 AM lambda n, right? How do I find the constant term A naught? What's a trick to find it? I want to find, in general, this is a polynomial, like this is not linear algebra. I have a polynomial and I want to find the constant term. Yeah, put PT lambda 0. But then what is this? This is determinant of t minus 0 identity, which is the determinant of t. So the constant term is always the determinant. Okay. All right. Okay. Zoom people. PT always says, so yes, thank you. Maybe there's a delay or something. I have to. Anyways, so yeah, we will show that PM of M is 0, and we're going to multiply both sides by M inverse determinant. So this is your guy, right? And then you get your inverse. So you multiply both sides by M inverse. Okay, you see, I have this was M, so it became identity. I keep forgetting the identity. So this is the identity, M inverse. And this guy was Mn minus 1 times M inverse. So it became N minus 2. Okay, and this guy became N minus 1. All right? But now I can divide by the determinant and isolate for the inverse. So here's your formula. Okay? So if you want to find the inverse of your matrix, you can find it this way, by just computing powers. Now, in 2 by 2, this is immediate. So let me do the 2 by 2 example. So you use this formula, and let's look at this carefully. So again, I isolate for M inverse, I divide by the determinant, and all the other terms are dead, right? So I only have A1 identity plus A2 M. Okay. And so that's how you get this M, and this guy here is the this guy here is A1. All right. So you open this up, you know what M is, you know what the identity is, 3I. So this is 3300. And if you just add these two matrices, this is the inverse. Okay. Now, if you wanted to find the inverse with 2 to 3, you have to take the adjugate and then, which is kind of similar, and then you have to divide by the determinant, Kramer's rule. So, but anyway, so that's how you can find the inverse. And I did matrices, but of course this is general stuff, right? So it says that the inverse of a linear map can be found from this formula. So you will have -1 determinant of t in some representation. Okay, and then yeah, you have A1 identity on the vector space all the way to Tn minus 1. Okay, so that's a way to find the inverse of any linear map. It's kind of crazy. And yeah, I'll just write you. So you can even have n to be infinite. So if you end up working in physics, so you have this following amazing formula. So it was 1 minus t inverse equal to TK. Let me write it this way. So TK. So this is like a geometric series for linear maps. So I mean, this is more if you go into physics. All right, let's prove Caley Hamilton. Zoom people, okay? So at least be able to get the inverse for 2 by 2, okay? So if you have a trouble for 2 by 2, please come talk to me just to make sure you can do it. Let's prove Caley Hamilton. So your guy splits the polynomial. So you can write it in this form. So I did a lot of stuff here, so let me explain. First, you know your PT lambda splits. So you can write it as lambda minus lambda I, or lambda I are in the reals. Okay? Because that's the one we care about for complexity. So you do it like this, and then you plug in T. So you get, I'll do it here. So you get PT of T, which I just write as PT because it's annoying, is the following operator. Product of T minus lambda I identity matrix. This is an operator. It goes from V to V. Right? Okay, good. So that's why I put an X here. This X is in V. So this guy is an operator. All right, good. All right. So, okay. So, yeah, why do we need that split result? Because one thing we proved is that when it splits, you have a chain, right? So, which is the same as saying upper triangular. And we're going to need this representation to prove this theorem. So that's what we just proved. When you split, you have a chain of T invariant subspaces. Yeah? Okay. Yeah, so that if this is the case, then you have this amazing formula. I mean, the formula is the main thing. I wish they stated it this way, and that's what's amazing. That you have almost eigenvectors plus some correction. Okay, you see how we use this. All right, so what are we trying to prove? We're trying to prove that this guy here is the zero mapping, right? So it's 0 for all x. Okay, so let's do it step by step. So, okay, let me ask you this. If I show it for each x1 to xn, why do I get, why this imply this? Just to see the linear algebra skill. Zoom people, you can say as well, why do I get from here to here? You two always talk. How about the other folks? Zoom people, any idea? Doesn't have to be right. You can. What's your feeling? Yeah. So you write your x in terms of the xi, and you take pt of x, and then you have ai of ptxi. Oh, yeah, okay, thank you, Shashwat. Yeah. Sort of one of the t minus lambda is 0. I have to think about this. Oh, yeah. But that would be, that's right. That's another way to do this. Yes. We will do it in the proof. Thank you, Sakura. But yeah, you can, right. All right, yeah. So you just go over the basis elements. Because each of these maps is a linear map. So you can just, okay. So this is 0. I mean, because I see people trying to compute adjoints, and I'm like, you can just work on the basis, right? You don't have to like kill yourself. Generic elements. So this is a good advice. Always work with the basis. If there's one thing that will stay in linear algebra in your head is don't work with generic elements. Find a good basis and then start your work. It's like, don't formulate a hard problem. Make it easier and then work by picking a good basis. That's like the one lesson in linear algebra. Right, the base case is immediate. But I still have to do it. So namely, I have to show that pt of x1 is 0. Okay. So I have to show that. But from here, we have the following result. We have that tx1 is equal to lambda 1 x1. Okay, that's the base case. Tx2 is lambda 2x2 plus some w1. But at least in the base case, it's just a negative. And so, can somebody tell me from here why I get 0? It's a little bit tricky. I don't know if you can see. Yeah, it's tricky. It's tricky. So you have to do this a little bit by hand. That these guys in fact commute. So you can bring the t minus lambda 1 all the way to the inside. So, yes. No, but by then it will have been some different element. Yeah, so it's not, so you need, I mean, there might be a way, I don't want to say no, like clearly it's the 0 map. So there might be a way to be able to do this. But let me talk about this commutativity. And I'll do, it's just brute force. There's no like, so let me just do 2 of them. And then it's by induction, okay? So you have to open it up completely. So you have t squared. So you do this with this with this. And then you do the lambda. So lambda 1 it, and then plus lambda 1 lambda 2 t. And then you regroup them the other way. So, I mean, I can do it here. So t squared, you just change the lambdas. So you put lambda 1 it here, lambda 2 it here, and then lambda 2, lambda 1 identity. You see, all I did was I swapped real numbers. So I swapped these 2, and I swapped these 2. And then you just regroup it. In a way, I'm just relabeling the aggregate. So then you get back t minus lambda 2i and t minus lambda 1. Okay? That's the trick. I mean, and you can do this by induction. So anyways, I think this is something you can do. It's not hard. Okay, Zoom people. All right, so they commute because you can relabel things and you get t minus lambda 1 x1, but then this is the zero map. So t minus lambda 1 identity x1 is 0. Okay, perfect. So we commute the operators. So okay, I'm doing it here. Commuted, and I just want to ask you some questions. All right. Now we have our induction hypothesis. Namely, you know that they're all 0 up to here. And then you want to get the WK plus 1. So, okay, so you take some V in WK plus 1. You want to show that PT of V is 0. Okay? So that's induction. So, yeah, so I take some, this is xk plus 1. Okay, type it. So take xk plus 1. So you have this formula. Okay. And oh, I see. No, it's not a typo. Okay, I'll come back to it. No, this is V. Anyways, so first I want to show you that this guy is 0. And maybe I can ask you, do I have the question? Right, okay, good question. So can somebody tell me where does this t minus lambda ixk plus 1 belong to? And the answer is in this one. Anybody can say it, Zoom people. Why is this? Where does it belong? In what space? Where else? Yes. What? Yeah. So this guy here is equal to yk from this formula. So wk. And can you even tell me why this is tau 0? Why this this will be 0? Right. Perfect. So now you use your assumption. And so you call this guy V from here, and V is in WK, and PT of V 0. Right. So, but again, this is not immediate. So you take a generic element, right? So you have PTV, but then V is of the following form, AM, XM for M1 to K plus 1. And then again, you use linearity. So you have M1, K plus 1, AM, PT of XM. And we just showed that up to K plus 1, they're all 0. Because we killed the basis elements. Right, almost done. Anyways, that's the result. So now let me warm you up for Friday. So we have not meet for Friday, I mean the class with in lieu of proving the Jordan block theorem, which is this guy. You can write everything in boxes with 0 everywhere else. We need to learn more about nilpotent. That's why you did nilpotent in your homework. Because we need to use them for this theorem. So just to remind you, nilpotent, it just means that you can find some power so that your map will be the zero. Okay. And let me warm you up. So we proved speckle theorem, and this is the beautiful picture of speckle theorem. Namely, you can, you give me any vector space, I can decompose it into directions where my guy is linear. So if you go into statistics, this is called PCA. So you give you some crazy data set, and you're responsible for finding directions where your guy is linear. Okay? Like, here's a crazy picture, or if you take any course, you will see. So, and you have some transformation, and people, you see pictures like this, where you pick the direction where all your vectors are moving linearly. So it stretches them this way and contracts them this way. You see this ellipsoid gets contracted. Okay, anyways, we'll talk about this, but it turns out that there's a general theorem, we'll do it starting this Friday, that you can still prove this decomposition for some general maps. Anyways, we'll talk about that. Yes.
If I can get like algebraic, so if you get like for one like one eigenvalue, it doesn't guarantee that those are orthogonal, right? We have to orthogonalize those ourselves.
Right, yeah.
Oh, okay.
Yeah, yes.